Functional groups is going to be the topic of this lesson, and a functional group, simply put, is something that adds functionality to an organic molecule. And when we say functionality, I mean it's going to alter the physical properties and the chemical reactivity in a characteristic way. Now, alkanes themselves are pretty unreactive. They do combustion and a few other reactions, but not really much for chemical reactivity for alkanes. But these functional groups are going to have added reactivity in comparison to alkanes, and in characteristic ways. So we'll talk about 10 different functional groups. We'll look at how you recognize their structures and how you name really basic examples of these different functional groups. Now, this lesson's part of my high school chemistry playlist. I'm releasing these lessons weekly throughout the school year. So if you want to be notified every time I post another one, or when I get around to posting my next playlist, subscribe to the channel, click the bell notification. All right, so I want to just remind ourselves about alkanes here. And you've got an alkane if you've got all carbon-carbon single bonds and nothing but carbons and hydrogens in your molecule. So it's a hydrocarbon with all carbon-carbon single bonds. Now, we kind of look at alkanes again as being the absence of all functional groups. And if we look at how we name them, being that it's called an alkane, we're going to name this 1, 2, 3, 4 carbons. Bute was our suffix we learned in the last lesson. And then you just end it with the ane ending corresponding to the alkane. And what we're going to find is that we're going to have 10 different functional groups we'll look at. There's more than that out there, but we're only going to look at 10 of them. And we're going to find that it's going to work in a similar fashion, that part of the name of the functional group is going to be the suffix we use at the end of the name. So there'll be one exception to that, but the other 9 are going to, I should say there'll be 2 exceptions to that, but the other 8 are going to kind of follow that pattern. So let's take a look at this. The first functional group we're going to look at is actually going to be now an alkene. So in an alkene, we learned in the lesson on hydrocarbons, is going to have a carbon-carbon double bond. So here we're going to put in a double bond. Now we have to do more than this, and if you look, this carbon right here and this carbon right here, they're both violating the octet rule. They have 5 bonds and 10 electrons around them, and that's why we're going to have to get rid of a couple of hydrogens to make room here, and that's why this is no longer considered saturated. It no longer has the maximum number of hydrogens possible. So, but now we've got this alkene here, and when you go to name an alkene, so you're going to end it with, it turns out, the ene suffix instead of the ane suffix. So we need to change one letter right here. And so instead of butane, this is now going to be called butene. But we've got one other part to this. So, because it turns out that carbon-carbon double bond didn't have to be at the end. It could have been, like, say, in the middle of the molecule. Or there's, lots of positions it could have been in larger and larger carbon chains. So you got to give its location as well. And what you want to do is you want to number your longest continuous carbon chain. Same thing we went through with alkane nomenclature in the last lesson. But you want to number the longest continuous chain that the double bond is a part of, and number it in such a way that you give the alkene the lowest numbers possible around it. So instead of numbering left to right, then we're going to number this one right to left. So 1, 2, 3, 4. And in this case, we can see the double bond is between carbons 1 and 2, and you always give it the lower of the 2 numbers. So in this case, we're going to use carbon number 1, and right before you name the parent chain, that's where the 1 goes. And so we're going to call this 1-butene. Now, if we had a methyl group coming off somewhere, like say coming off carbon 3 or something like that, we'd put the substituents before the parent chain, and maybe we'd say something like 3-methyl-1-butene. But I'm not going to go with any branch structures in this lesson. We're going to do very simple examples, and that's likely all you're going to encounter for a lot of these functional groups anyways. All right, so that's 1-butene. Now we've named alkenes. So the next functional group we want to take a look at are alkynes, and alkynes are going to have a carbon-carbon triple bond. So, and in this case, now we're going to change this to a yne suffix for alkynes. And so once again, part of the name of the functional group is what we use as the suffix for the parent chain here. And so in this case now, instead of a double bond, and we'll get these numbers off. It turns out we'll put the exact same ones back on. But now we're going to have a triple bond instead. And actually, I want to make that look a little prettier. Cool. And to make room for that, we got to get rid of yet 2 more hydrogens as well. So this is now butane. And butane, again, we've got to give the location. And once again, we're going to number the longest continuous chain that the triple bond is a part of to give it the lowest number. So once again, we're going to go right to left. And so this is 1-butane. We'll give it that lower number yet again. So alkenes and alkynes named very similarly, it turns out. And one thing you should know here is that it's the pi bonds. So it turns out pi bonds have a certain reactivity with them. They're higher energy electrons than sigma bonds, than the single bonds. And so there's some reactivity associated with them. And it turns out alkenes and alkynes can do what we call addition reactions. So, and I'm not so concerned about that, but I did want to point out that these do have a chemical reactivity, both alkenes and alkynes, that alkanes do not have. So the next functional group we're going to look at is the alkyl halide. So, and it turns out the alkyl halide is an example of an exception from everything else we've kind of looked at here and stuff like that. So it turns out that these are not named with a suffix as part of the parent chain. They're always going to be named as a substituent, it turns out. So the same way in the last lesson we had like methyls and ethyls coming off the parent chain like butane or pentane or something like that. In this case, as halogens, you name them as halo substituents. So that could be fluoro, chloro, bromo, or iodo. So what you want to do is number your longest continuous chain that they're attached to. So in this case, that's these 3 carbons, and I'll number it right to left to get the halogen substituent, the lowest possible number. And in this case, then, 3-carbon chain is going to be called propane, we learned in the last lesson. But in this case, we're going to say that we have a chloro substituent attached at carbon 1. And so we'll name the substituent first, and so this is 1 chloro, and then the parent chain is just simply propane, and it's one big long word, no space there or anything like that. So, and this is indeed 1-chloropropane. And once again, so this is what we call an alkyl halide, and it turns out they can undergo what are called substitution and elimination reactions, which again is not the most important thing, but I just wanted to point out that this functional group adds some sort of chemical functionality to this molecule that would not have been present in an alkane. All right, so the next example of a functional group we want to look at is called an alcohol. So and notice when you use the word alcohol in everyday life, you're probably meaning like, you know, the alcohol you clean a wound with, which technically is isopropyl alcohol or isopropanol, or perhaps possibly the alcohol that's in like beer or wine or something like that, and it turns out that's ethanol or ethyl alcohol. But alcohol is a much more general term in organic chemistry. It describes a broad class of molecules that has one of these OH groups right here. So, and we call that OH group an hydroxyl group. So, and generically, your alcohols are going to kind of have this general pattern here. You'll find out that we use R here to kind of represent any carbon chain of any length. So it could be a 1-carbon chain, could be a 100-carbon chain. So that's what kind of R on your handout refers to in most cases. In the case where it could be a carbon chain or a hydrogen, I specify so. All right, so this is an alcohol here, and the way it works here with an alcohol is part of the name alcohol is going to be the suffix at the end of your parent chain. And so in this case, we've got a 3-carbon chain, and that's propane, and I'm going to write that out for a second. So that's propane. And what we want to do here then is add the ol suffix at the end of that. But they don't want to put this crazy weird vowel thing with EO. And so it turns out we're going to take that E off, and then we're just going to add that ol or ol suffix. And so this is a form of propanol. But that OH could have been attached at the middle carbon or something too. And so we've got to number the chain, and we want the longest continuous chain the OH is attached to, and number it from the side that gives it the lowest possible number. And so in this case, we'll number it right to left. And so this is not just propanol, this is, put it right at the beginning of the parent chain, 1-propanol. And once again, if you had any other substituents like a methyl coming off carbon 2, well then we would have said 2-methyl-1-propanol. But that is the name of the parent chain there. And the key was that when you have an alcohol, it's going to be named with that OL suffix at the end of the parent chain. Now, it turns out these alcohols, one, because they have an OH bond, they're capable of hydrogen bonding. They typically have higher boiling points and stuff like this. And then there's a whole host of characteristic reactions that are unique to alcohols, and some are substitution, some are elimination, some are oxidation. And again, I'm not super concerned that you know any of those and stuff like that, but again, I just want to point out that having an alcohol does lend some functionality to this molecule that once again was not present in an alkane. All right, so the next one here we're going to talk about is going to be related to this, but it's not going to be an alcohol. We're going to see it's going to have a similar structure, but it's going to be what we call a carboxylic acid. And it turns out, when you think of an organic molecule, it's going to be an acid. It turns out it's going to be this carboxylic acid. That's part of the functionality that they're going to have. And it's going to get a different suffix, it turns out. So we're going to take that off. So, but in this case, what's going to be different about this is you want to look at the carbon specifically that is bonded to the OH. And you want to take away those hydrogens and instead give it a double bond to oxygen. Now, it turns out when you have a double bond to oxygen, so a carbon-oxygen double bond, we refer to that as a carbonyl group. So in the same way that we referred to an OH as a hydroxyl group, that's called a carbonyl group. It itself is not a functional group, but it's a part of several different functional groups, the carboxylic acid being one of them. So the carbonyl group and a hydroxyl group are both part of a carboxylic acid. And so the general formula of a carboxylic acid is always going to have that carbon-oxygen double bond with that exact same carbon. It can't be a different carbon. It has to be the same one that's double bonded to oxygen being also bonded to an OH. And it turns out having that double bond to oxygen right next door makes this much more acidic than an alcohol. And it makes certain chemical reactions possible that don't lend themselves well to alcohols. And so there's some functionality that's different than alcohols, and we've got to give it a different name, and they called it a carboxylic acid. Cool, now we named this thing, so it turns out that the ic acid is actually the suffix, or at least most of the suffix that goes on the end of this. And so in this case, I'm going to take off that one for a second. So it turns out that for a carboxylic acid, because part of the functional group, it has 1, 2, 3 bonds out of carbons 4. So as a result that are part of the functional group, it always has to come at the end of the chain. There's only room for one thing to be attached. It's always going to be at the end of the chain, and so it's always going to be attached at carbon 1, which is why they decided, well, then the 1's not necessary. Every carboxylic acid would be named with a 1. So we're not going to put the 1 in front. So, and the suffix, it turns out, is not just ic acid, but it turns out they chose oic acid, and so this is propanoic acid. So, but what's nice again is that, if I gave you a name, propanoic acid, if you looked at your list of functional groups you're supposed to know, you'd probably look up and be like, yeah, that's a carboxylic acid. It makes sense based on the name that it's a carboxylic acid. But once again, you also got to be able to identify it based on the structure as well. And then once again, this has some functionality that is distinct from the other functional groups, including functionality that alkanes doesn't have, which is why it gets its special name as a functional group here. We're going to see the same kind of pattern here where if you put a carbonyl right next to some other group, it often changes it into some brand new functional group. We'll see that in at least one other place here as well. All right, so next on the list here is going to be an aldehyde. And we're going to find out it looks somewhat similar to a carboxylic acid here, except instead of an OH right there, it's just going to have a hydrogen attached to that carbonyl carbon. And so this is another carbonyl containing functional group. Generically, it looks like this. On the other side, you've got to have, any kind of length carbon chain you want here. Turns out it could even be another hydrogen technically, and we call it formaldehyde, but most aldehydes are going to have multiple carbons in it. And in this case, if you look once again, we're going to take part of the name of the functional group itself, in this case it's the Al, and use that as the suffix at the end of the name. It's also true that, that this functional group takes up 3 of carbon's 4 bonds, and so you can only ever be bonded to one other thing. And once again, the aldehyde carbon is always going to be at the end of the chain. It's always going to be carbon number 1, which means it is not included in the name. This is just propanal. That Al suffix is sufficient to tell us it's an aldehyde. And once again, if I gave you the term propanal, you might have to look through your functional groups if you were not up on them, but probably at the end of the day, you might see aldehyde and be like, oh yeah, that's propanal, must be an aldehyde. From the gist there. But once again, you also got to be able to recognize it from a structure as well. So the next one we want to take a look at is what we call a ketone. And we'll find out that ketones and aldehydes have some similarities. Now the difference here is going to be that instead of the carbon-oxygen double bond being at the end of the chain, we're going to find out that the carbon-oxygen double bond is going to be in the middle of the chain. And so we're actually going to change both sides to be in red here. So the carbonyl carbon here can't be bonded to a hydrogen on either side. It's got to be bonded to carbon chains on both sides. It has to be specifically carbon chains. It can't be some other atom either. And so everything's there is important. So I need to doctor this structure then quite a bit here. And so we're still going to have a carbonyl, but now it's got to be in the middle of the molecule, not at one of the ends. And it has to have a carbon chain on both sides. And so now this is an example of a ketone. And it turns out when you go to name this suffix is going to have the O-N-E. And so this is going to be propanone, which again, you could probably tell from the name if you just had to look at the list of functional groups, like, oh yeah, ketone. Propanone's probably a ketone. Now that's not sufficient. What you want to do is, once again, this carbon-oxygen double bond could be located in longer molecules at a variety of different positions. And so you've also got to give me the chain locator of where it's located at the beginning of the parent chain. And so in this case, you want to number the longest continuous chain that contains the carbonyl carbon in such a way that it gets the lowest possible number. Well, in this case, whether we go left to right or right to left, it doesn't make a difference. So I'm just going to go left to right, but either way it would have ended up at carbon number 2, and that's why it didn't make a difference. This thing is symmetrical. And so it turns out this is not just propanone, this is 2-propanone. Cool. Now, it turns out aldehydes and ketones having this carbon-oxygen double bond in the way they're structured and no other electronegative atom associated with it, it turns out they actually have similar reactivities. In an organic chemistry class, we'd actually teach a chapter on these two functional groups together, and it turns out that this carbon is partially positive and being double bonded with that oxygen that's very electronegative, and that adds some functionality to it. It turns out they do a characteristic reaction called a nucleophilic addition reaction with a variety of different reactants that it might react with and stuff. And again, the type of reaction it does is not the most important thing in the world. What I really just wanted you to see is that once again, there's a functional group that is leading to this molecule having some sort of characteristic functionality, chemical reactivity associated with it. So our next functional group we'll look at is called an amine. So, and in this case, amines, ammonia, they're kind of derived from ammonia, and they're very fishy smelling. And the reason they're fishy smelling, and really we should say that it's not that amines are fishy smelling, it's that what's on the skin of fish is more amine-like, and that's why they're fishy smelling. So common amines here are actually good bases as well. So when you think of an organic molecule that's acidic, again, the functional group we usually associate with that is probably going to be a carboxylic acid. When you think of an organic functional group that is a base, this is the one we usually come up with, an amine. And so it's our first nitrogen-containing functional group, and in this case, that nitrogen is typically going to have 3 bonds. So and at least one of them needs to be to a carbon chain, but the others could be a carbon chain or a hydrogen. So carbon chain or a hydrogen. So in this case, I've got a nitrogen bonded to just 1 carbon chain and 2 hydrogens. So that's an example of amine, but it could be bonded to all 3 locations, could be carbon chains as well. Now, for a simple amine like this, you want to find the longest continuous carbon chain it's attached to and number that carbon chain in such a way that he gets the lowest possible number. And so in this case, we got 3 carbons, and if I numbered it left to right, he'd be at carbon number 3, but if I go right to left, he's going to be at carbon number 1. Now, he didn't have to be at carbon number 1 in principle, he just is in this example, but nothing says I couldn't have attached the NH2 from the middle carbon or something like that. So don't think that they are always going to be at number 1. They're not. So they can be in a variety of positions along the chain, but we do got to say where they are. So as well. Now, turns out that the suffix we use on amines is just simply the entire name of the functional group, amine, and that makes it really easy. So this is just going to be propanamine. So propanamine, and since the nitrogen's attached to carbon number 1, we'll call it 1-propanamine. And that's how we'll name them. So cool. And once again, we've got our first example of a nitrogen functional group. And again, it's adding some functionality. And it's more than just basicity, but that's the only thing I really want to talk about. But it's adding some functionality to this molecule that wouldn't be present otherwise. Now, it turns out the next functional group is going to be a little bit related to this. In the same way we saw like alcohols, and when you add the carbonyl right next to the alcohol, you get a carboxylic acid. We're going to see something similar here as well. And so if I take the adjacent carbon, the one bonded to the nitrogen, and if I give him a double bond to oxygen, make him a carbonyl. Once again, this is no longer an amine anymore. It turns out now we would refer to this as an amide with a D here. And what's nice though is that it's also going to change the suffix over here. And it's nice they're going to use the entire name of the functional group once again and just say propanamide instead of propanamine. And so that makes it not so bad. The suffix is just the name of the functional group, and you could figure out just based on the name that, yep, that's an amide, and before it would have been an amine. So, and in this case, it turns out that your functional group here is going to have to be adjacent to a carbon-oxygen double bond with the carbon chain coming off there. So this is in principle, the parts of an amide now. And again, the carbon-oxygen bond has to be immediately adjacent to the nitrogen for it to be technically considered an amide. And in this case, because 3 out of the 4 bonds of that carbon are going to be tied up with the amide, it's only ever going to be bonded to one carbon chain. And so it's going to come at the end of the chain is really the key here. It's always going to be numbered as carbon number 1, which means you don't actually include the 1 in the name here. So with the amine, we had to call it 1-propanamine. But as the amide, the 1 is not included in the name at all. It's just propanamide. It has to be located at position number 1. Now, it turns out that these amides are not nearly as basic, and I say not nearly, actually, they're not basic at all. They're not bases like amines were. It turns out that this carbonyl decreases the basicity associated with a nitrogen atom to where it's not really considered a base. And so it turns out they undergo what are called nucleophilic substitution reactions. But they're not the most reactive things in the world, and that's good because amides are actually the kind of bond that link your amino acids together in your proteins, and we want those to be stable. We want those to kind of like be lock-solid bonds that aren't going to break really easily inside your body and stuff like that. So it's kind of nice that these are not the most chemically reactive things in the world, but they will, under the right conditions, do what's called a nucleophilic substitution reaction. But again, the type of reaction it does is not so important. I'm just once again showing you that there's some unique functionality associated with this functional group. So the last functional we're going to take a look at is called an ester. So in this case, you're going to have a carbon-oxygen double bond, carbonyl, and it's going to be bonded to an oxygen right next door, but not just an OH. That would be a carboxylic acid. It's going to be an oxygen that's bonded to yet another carbon chain. And so you've got a carbon chain on this side that's bonded to the carbonyl side, but you've also got another carbon chain bonded to the oxygen side rather than a hydrogen. Again, if this was just a hydrogen instead, this would be a carboxylic acid. We already named those. But this is what constitutes an ester. And so in this case, you've got to have an R group on both sides. And in this case, I can call this like R1 and R2 because they don't have to be the same length at all. They can vary and stuff like this. And so these esters, it turns out, come up in a variety of places. You find these in your lipids. So as one concrete example you'd find in your body. So it turns out your triacyl glycerides have 3 ester bonds in their structure. And just like amides, it turns out these also do nucleophilic substitution. In fact, we often teach a chapter that include esters and amides and carboxylic acids sometimes, all in the same chapter for some of the similar chemical reactivities they do. But they all have this carbonyl group right here. So, and then next to an electronegative atom, which gives them some similarities in the types of reactions they would do. Now, if we're going to name this ester, turns out the name ester is probably not going to help you remember how they're named. This is one that actually has nothing to do with that word, unfortunately. But the way this works is you have to kind of break this up into 2 pieces. And you want to break up one piece is the carbon chain bonded to the oxygen is going to be the first word you use. And in this case, this is just 2 carbons, that's eth, and we're going to name it as an ethyl group. So we'll just get rid of that altogether. So we'll call this an ethyl group. And that's the first word. It's just named as an ethyl substituent. And then we're going to name the second part right here. So, and it turns out that this kind of looks almost like a carboxylic acid if that were an OH. Well, the carboxylic acid would have been called, again, 3 carbons, propanoic acid. Well, it turns out this looks like the conjugate base where you've lost the H, and oftentimes what we do is we turn the ic into an 8. You might have seen this with like the some of the polyatomic ions like nitric acid versus the nitrate ion, or perchloric acid versus the perchlorate ion. Same thing here. We're going to have propanoic acid versus the propanoate ion. And so it turns out that's going to be named as propanoate. And so the ic that was on propanoic acid turns into an 8, and so it's propanoate instead, and that's your second word. And so the name of this ester is ethyl propanoate, and like I said, there's no relation to the actual name of the functional group in this one example. So we saw that with alkyl halides, we've now seen it with esters, but for the other 8 functional groups, part of the name of the functional group itself is going to show up in the name. So, but a couple of them, you're going to have to do just a little more memorization to be able to look at a name like this and be like, oh yeah, that's what an ester looks like. It always ends with O8 as the suffix, things of this sort. Cool, and that's our discussion on functional groups. There are a number of other organic functional groups that do exist, just none we're going to talk about in a high school class. And the truth is, even in a typical year-long organic chemistry course in college and university. We would only actually discuss a handful more anyways. So, but there are quite a few others that exist. Tried to kind of show where some of these actually exist in your body in different places, like in proteins or in lipids and things of this sort. But once again, the whole idea behind a functional group is that it adds some sort of functionality to your molecule, either physical properties and or chemical reactivity. And once again, you're going to need to be able to recognize them in a molecule. You might get a molecule and be like, yep, that's an ester. Or you might also be given a name and say, oh, yep, that's an ester. Or on the odd chance, you might have to actually name an example, a very simple example of one of these different functional groups. Now, if you found this lesson helpful, would you give me a like and a share? One of the best things you can do to promote the channel and make sure that other students get to see this lesson as well. If you are looking for the study guide that goes with this lesson, if you are looking for practice problems on organic chemistry here, check out my premium course at chadsprep.com. A free trial is available.